Looking at today. Work, energy, and power. What is this? Okay, so work. We're gonna define. Well, not we're gonna define, but it's defined in like the physics and the scientific world as a force through a direction. That's what I want you to take away from this. The energy transferred when a force is applied on an object through a distance. Sorry, not a direction, a distance. So work is a force through a direction. This is the formula that we're going to use to calculate work. Work is energy, so that's how much we're gonna, or that's how we're gonna calculate the energy expended when we do something. And the force has to be parallel to the distance that you're traveling for whatever, like if you're moving an object. If you're pushing an object from the side and it's not moving at all, you're really not doing any work, even though it feels like you're struggling because it's so heavy. I don't know. So that's what this is saying. It's is only done when the force is parallel to the distance that you're moving. The standard units for was international standard unit. The standard unit for work energy it's energy is 1 joule, and a joule is defined to be 1 Newton of force times the meter. So it's 1 Newton meter. Let's continue on. Ooh, look at that! That's nice. He's moving a ball. So, an example. A student lifts a 50-pound ball 4 feet in 5 seconds. I don't know why it says, actually I do know why it says 5 seconds. But a 50-pound ball 4 feet. So how many joules of work did the student complete? Well, we use our formula, the force, which will be the weight of the ball, and because we have to move that weight, and we're moving it 4 feet. So we'll take the force times the distance. The force would be 50 times 4. So that's what we do here. But I was looking at this. So the answer is 200 foot-pounds, but foot-pounds is not the standard unit for energy, for work. So what do we got to do? We got to convert it. This is it's not in standard units of joules, so first you have to convert. For this, I don't know why they write it like this. It should be like 1 Newton divided by, this is probably the way you've seen it if you're converting units, 225 pounds. You want the pounds to cancel out, so they're taking the conversion. 1 Newton is the same as 0.225 pounds, and they're multiplying that conversion, and they're using significant figures of 3. Now the pounds cancel out, and then you just are left with newtons. So I would write it up and down. That way you know that the pounds cancel out. This is the conversion. So anytime you want to convert units, you have your conversion as a fraction. 1 Newton per 0.225 pounds. If you want the pounds to cancel out, you make sure the pounds are on the bottom. If you want the newtons to cancel out, then you'd flip this fraction over. That's all for that. So if we convert 50 pounds into newtons, we get 222.5 newtons if they're rounding to significant figures of, well, I guess that's 4. Well, maybe they're not rounding. I don't know. And then 4 feet, this is also the conversion. You just write it up and down just like that. 1 meter is 3.28 feet. So 4 feet is 1.22 meters. And then we can continue on. Now we can do the force, which would be newtons times meters, newton meters, and newton meters are the same as joules. So you get about 271 joules of work to lift this ball. Looks like the sun? No, looks like it's okay. Moving on. Energy is the ability to do work. So there's many forms of energy. Light, heat, mechanical, chemical, and electric forms of energy can all be used to exert a force for a distance. Force through a distance, that's what I would say. Like a roller coaster, this has, well, I guess you could say mechanical energy. If you start up at the top, that's potential energy, and then you're falling due to the force of gravity. This guy looks sad. Look at him. He's about to cry. This solar sail, I was like, what's a solar sail? And then I looked it up, and
I'm Fraser Kane.
well, maybe we'll talk about this a little bit. Solar sail is pretty cool. Maybe I'll show that video. I don't know. Maybe I shouldn't. This, you can convert light energy into this. Light actually moves a solar sail, which is pretty awesome. And then there's like fuel cells. Yeah, I do want to watch that because I didn't understand it.
And I'm a sailor.
He's not a sailor.
Okay. I've got
cold.
a sailboat that I take out on the water when it's warm and the weather's nice here.
Can you even hear that?
Island. I think it's one of the reasons I absolutely love the idea of a solar sail. Here's how they work. Light is made up of photons. Even though they have no mass at rest, they have momentum when they're moving, well, at light speed. When they reflect off a surface, like a mirror or a shiny piece of metal, they impart some of this momentum to that surface. This effect is negligible here on Earth, but out in space, with forces perfectly in balance, that additional momentum can really add up. A spacecraft flying to Mars gets pushed off course by several thousand kilometers because of light.
All right, that's enough of that. So light actually moves a solar cell. So this, I think, is a solar cell. It has to be really, really thin and really, really light. And then when light hits this, it pushes it like a sailboat. Like the wind moves the thing. Okay, moving on. So that's that. Potential energy is oh shoot, I forgot to time this. Potential energy is energy that's stored. It's there's a couple of different ways that you can store potential energy. If you just have an object that's really high, that's gravitational potential energy. The force of gravity could move that through a distance. That looks like bark. I don't know what that is. Oh, those maybe rubber bands, I think. Maybe. I don't know. Looks like oatmeal or vomit. He's got glasses. And like chemical potential energy in the chemical bonds. Here's some dirt. I don't know. Moving on. Kinetic energy is the energy of motion. I think you might have heard this if you've ever taken physics. Energy which a body possesses because of its motion. So anything that's in motion has kinetic energy. Yeah. Look at those pictures. Nice. Energy transformation. So what we can do as humans is we can eat food and then we can play lacrosse. And that's all that we can do. There's nothing else that we can do. No. So there is chemical energy in the bonds, the chemical bonds in food. Our bodies are able to break them down into sugars, and our muscles use those sugars to convert it into kinetic energy. We can move. You can get sunlight, radiant energy, and through the process of photosynthesis, plants can make you wear a hairnet. No, plants take that energy, take that energy and they use it to grow, and then we eat the plants, and we can, and then same thing. We're just monsters. We just consume everything. And then electrical energy makes chicken. All right. Renewable energy sources. We already talked about this through our presentations, which was kind of cool. Biomass. If you take any grown stuff and convert it into like fuel for cars or something, that's one way. Hydropower, like dams, or I guess wave energy. I forgot what that was called in whoever's presentation. Geothermal energy takes the energy from the tectonic plates rubbing together and making heat. We convert that heat into, put it through a turbine and create electricity. Same idea with windmills. And we learn about stuff with the solar panels. That's probably the coolest in my opinion. Non-renewable energy sources. We already talked about this. There's Doc Brown. Have you seen Back to the Future? It's red. Look at that. Uranium is red. Why? Because. All right, moving on. Conservation of energy. These are the first two laws of thermodynamics. So energy cannot be created or destroyed. It can only be transferred from one form to another. So a lot of the time, like when we maybe burn gasoline. We use the energy in like a combustion engine. It moves a piston, and we create that that changes to mechanical energy, and then powers our cars. But a lot of it is, we say lost in quotations, a lot of it is lost through heat. A lot of the energy gets lost through heat and sound. Sound is also a form of energy. So yeah, that's why the exhaust, we say it's lost because it's not usable anymore. We want to make the car go. We want to move it through a distance. So we break the chemical bonds in the gasoline when we ignite it, and then we use it to go forward. But a lot of energy gets, I guess, lost in through the sound and heat. When energy is lost to heat, it's when the input energy is changed to output energy, and some of the output energy is not usable in the way that we want to use it. That's why we say lost. I think I'm going to pause this and go on to part 2, starting with this slide. I got to stop this. Stop.